Today I wanted to finish off doing chapter 10, so the strain gauge. I wanted to do a problem on the strain gauge rosettes, right? And then we're going to skip chapter 11 and go into chapter 12, which is beam deflection. So the last two chapters are 11 and 12, which are beam deflection and column buckling. They're actually not that hard, but it just kind of have to do a little bit of reading. So I posted the readings and the homeworks on, obviously the homeworks are mastering, but please look at the post for the week on Blackboard because it explains how each problem should be done, okay? Because there's a couple different ways to do some of the beam deflection problems, okay? So that's mentioned in there. All right, well, let's get started. So I wanted to first do, I wanted to quickly finish off chapter 10, right? So let's go to the whiteboard thing. All right, so if you remember at the end of last class, I kind of derived how you get the relationships between different oriented strain gauges. Remember, the strain gauge only reads a normal stress, and how you can get the planar state of stress from those. So we did the 0, 90, 45, and I also posted on Blackboard the 0 plus or minus 60 orientation as well, which you'll see is the same as the 0, 60, 120 or whatever it is. You'll see they're really the same, okay? So let's do an example here and you can see how it kind of goes. It's not that big of a deal. So this problem here, they give you a strain gauge rosette as shown here, and it's on a shell element. So they say a shell element. So this is like a thin wall pressure vessel. So the assumption is you really only have planar strains, okay? And they give you the readings for strain gauge A, B, and C, and they want you to determine the principal strains, the in-plane principal strains, okay? The reason they say in-plane is because actually, since it's reading strain, if it's a shell problem, there will actually be a small contraction in the plane, and that would actually give you a non-zero Z component of the strain, but it's pretty easy to pick those out. For calculating the stresses, it actually will not make a difference. But anyway, so here it goes. All right, so right there are the values. So last time we looked at a strain gauge orientation that was in the 90, 0, and 45. And the way I labeled that in class, if I remember correctly, is I called this like A, B, and C. So it's a little bit different, but you can see it's just rotated, right? And when we did this, we were able to get, obviously, if this is the X direction and this is the Y direction, the normal strain in the X direction is just what we read off of strain gauge A. The normal strain in the Y direction is what we read off of strain gauge C. And the planar shear strain, the gamma XY, is going to equal 2 times what's read on strain gauge B minus what's on strain gauge A minus what's on strain gauge C. All right, so that's for this particular case. That's exactly the way we derived it in class. Oops, there's the strain gauge. Okay, so now in this particular case, obviously they've labeled them a little bit differently, okay? And obviously it's oriented 45 degrees. So that's fine. So I'm just going to call this the X direction, and let's call this the Y direction. X does not always have to be parallel to the floor or whatever, to the edge of the book, but we'll do it that way. And if that's the case, just swapping the letters, right? We know that the normal strain in the X direction off the above rosette is what's read off of the strain gauge label C, and that's going to be 250 microstrains, okay? The normal strain in the Y direction as shown there is what's read off of strain gauge A, and that is minus 200 microstrains. And then the shear strain in the plane is going to be what's read off of the intermediary strain gauge, B, minus A minus C. And so if we do that, that's 2 times 300 microstrains minus the 250. Well, I should say actually 2. I should get it the same way. Minus the minus 200 minus 250. Okay. And that gives me 600 plus 400 is 800. So it's 550, right? If I did that correctly. Positive 550. 600 minus 50. Yeah, 550, right? Okay. So now we know the strain state, in this orientation, right? So what's actually happening? It's stretching a little bit in the X direction. So it's going to stretch like this, right? Oh, that does not look like a stretch. That looks like something weird. So it stretches in the X direction. It compresses in the Y direction. All right. So before we apply the shear, the little element looks like that, right? And then once we shear it, it's going to have a positive shear on the XY direction. So it's going to shear up. And so that means that basically it's going to look something like this. Whoops. All right. So that's what it's going to be in that particular orientation, right? And in this case, I don't really need to know that. It's not like they asked me for the strain in the horizontal direction or in the vertical direction, right? Which I could do with a strain transformation, but all they're asking here is to determine the principal strain. So I can just as easily construct Moore's circle off of this data here, okay? So we'll use this strain state to write or to construct Moore's circle, okay? All right, so let's do that. So again, here is the y-axis is the shear strain, but remember we always divide the engineering shear strain by 2, and it's positive if it's shearing in the clockwise manner. On the x-axis, we are going to plot the normal strains, okay? And there we go. So let's first start on this face, if you will, okay? And on that face, we have the normal strain in the x direction. So that's the 250 here. Again, I'm going to drop the 10 to the minus 6 on Moore's circle, okay? So let's assume like 100, 200, 300. So 250 would put me about there. And the shear strain is the positive 550, right? Which what we showed here is sheared in the direction as shown, right? Now that is going to rotate on that face. That's going to rotate it, or the appropriate shear stress to do that type of shear straining is going to rotate it in the counterclockwise manner. So that means we go negative on that, right? So it's going to go down by 200. But remember, that is the shear strain divided by 2. So instead of going down 200, I'm sorry, we should go down 550, but remember we have to divide that by half. So that is 275. So if this is minus 100, minus 200, minus 300, minus 275 is about there. So that gives me 1 point on Mohr's circle right here. So that's at 250 minus 275, right? Again, remember, the shear strains are divided by 2. So this is actually what we call the tensorial shear strain. It's really the non-engineering shear strain. And usually people denote that as like epsilon xy. But this book doesn't do that, right? But if you take further classes in solid mechanics, they'll show you that that's what it is. Okay, so that's 1 point. All right, so now we need to get the second point. We'll use this face here, right? This top face. There we have a normal strain that's compressive. So we're going to go into, this circle is going to be bigger than what I have here. I'm probably have to move this. Let's see if I can do it just look, we need some more room. Okay, so we need to go negative 200. So if we kind of scale it to be about the same, that'll put us about here. And it's the same shear strain, but it's now rotating it in a clockwise manner. So we're going to go up positive 275. So I should probably 100, 200. Is that about it? It's about 100, 200, 300, right? So it puts us about 275. So that puts us right about here, okay? So again, this is gamma over 2, and that is clockwise positive. So this point here is going to be minus 200, positive 275, okay? That's that point. And then we can connect that up to give us the circle, right? So here's the diametric line. And then maybe I can try to draw a circle. It's gonna be something like that, right? That's probably not very well done, but you get the idea, okay? All right, so we want to get the principal strains. So that's where it intersects the x-axis, okay? So let's get the center of the Mohr's circle. So the center of Mohr's circle is going to be the average of 250 and minus 200. So 250 plus negative 200 divided by 2 gives me a positive 25, right? So that is my average strain. That's the center of Mohr's circle. 250 minus 200 over 2. And that gives me 25, right? So that's the center of Mohr's circle. Kind of looks about right. And let's get the radius, okay? So the radius here, we can get it, you want to get it off of this line here, this triangle. So this distance here is 275. This distance here is the 250 minus 25. So this distance is 225. So the radius of the circle is going to be the square root of 225 plus 275 each squared. And that gives me a radius of 355 microstrains, right? Right, so that is the radius. I guess it's fine. Okay, so now we can get the two principal strains, epsilon 1 and epsilon 2, just by adding and subtracting the radius from the center, right? So that's going to give me the first principal strain is the average minus the radius. So that is 25 microstrains minus the 355 microstrains, right? And that gives me a value of minus 330, right? So that's going to be to the -6 strain units, okay? And then the second principal strain is going to be the center of the circle, the average strain plus the radius, right? And so that's 25 plus 355. And that gives me 60, 70, 80, 380 microstrains. And so those are the answers. Obviously, you could also figure out the max in plane shear strain, which will be the radius times 2. It's the diameter of the circle, and then that'll actually also equal the max absolute, because in this case, the two other Morse circles for strain are those guys there. Okay, all right. Okay. Is there any questions on that? So the strain gauge results, the rosette is pretty plug and chug. Like I said, there's really only two configurations that you see, right? So even if you see, like, for example, you might have something that looks like this. Where this is 60 degrees and this is also 60 degrees. Okay. Now, if you have a rosette that looks like this, which this is 120 and this is 120, right? Let's say this is A, B, and C. A, B, and C. Those two are identical. They are the same. They behave exactly the same. This strain gauge B, which is oriented, you can see if you just take this strain gauge B and you slide it down here, you get this exact same configuration. It doesn't change the sign. It's still going to read a positive strain if it stretches or a negative strain if it compresses. So the fact that the strain gauge is here as opposed to here really gives you exactly the same answer. Sometimes you even see strain gauges that are done like that. And obviously, that is identical to having the middle strain gauge there. So they look a little bit different, but really either you have the 45 orientation ones or the 60-degree orientation ones, and you have both of those equations. So, you can derive them very easily, but you really don't need to. You can just use those equations, get the full planar state of strain, and then from that, either do strain transformation with the equations, or you can use more circles to figure out principal strains and all that sort of stuff. Okay. So it's not terribly difficult. All right. But strain gauges are a big deal. Still this day, people have been using them for over 100 years, but they're still the most common way to do stress measurements on structures. Okay. All right. Well, let's talk about beam deflection. Okay. I usually don't like to try to cover too many different topics in one class, but we're almost caught up. And I did cover the strain gauge stuff last time. So do I have my PowerPoint? No. Okay. Where is it? I already had it opened up. All right, like I said, this is going to be chapter 12 in the text. It's on beam deflection. Now, if you remember when we went through axial and torsion and yeah, just axial and torsion, right? Remember, we were always able to, like the last bit we did in both those chapters is we were able to calculate deflections and use those to solve statically indeterminate problems. When we did bending, you may or may not have noticed that we kind of punted on computing deflections, and we did not do statically indeterminate problems, and they're not in that chapter, and it's for a good reason in that to actually calculate the beam deflections, it's a little bit more involved. We do have to basically solve or integrate a differential equation. And we do need to be able to calculate beam deflections to be able to solve statically indeterminate problems. So we're going to talk about that now, okay? So it's basically enough details to it that they decided to give us a new chapter, okay? So let's see if I can share my screen. Maybe, possibly. All right, so okay, so chapter 12, beam deflection, right? So here's a very generic beam. It's pinned and it's got a little roller in the middle of it, and we got some force on it. P, you can calculate the shear diagram, the moment diagram, and you also are able from the moments calculate the bending stresses anywhere on this beam, right? So we already know how to do that. It's the same beam we covered in chapter 5, I forget what it is, 5 or 6 or something like that, right? But now we need to go find what is the deflection, okay? So when we describe this curve here is a plot, this blue curve, right, is a plot of the center line deflection. It's the deflection of the neutral axis. It's the deformed neutral axis of the beam. All right, so it deflects off of the neutral axis. And so we're going to call this distance here, the amount that it deflects, as a function of x, v of x. This is, oops, I was going to do this u. So used to call it u, but v of x. So if you were to know v of x and you were to plot it out, you would exactly get that blue curve. Sometimes they call that the elastic curve. That is the beam deflection curve. That is what we want to find in this chapter. So that's the deflection. We're also going to be worried about the angle change. I should have probably, let's say right here, here's v of x, right? At the same point we're doing the slope, right? Right? So we also might be concerned with this slope of the deflection curve at some point x. And so that is given by theta of x, right? And if you remember from calculus, the slope of the curve is very close to the first derivative of that curve with respect to x, okay? So the derivative of the deflection curve, the elastic curve, actually gives us the angle of the slope, okay? So there you go. So we have that relationship, okay? Which, from calculus, right? This is from calculus. Calculus, right? Or pre-calculus, or whatever it is, okay? All right, so that's our objective in this class. I mean, in this class. All right. So if you remember, which if you don't, it's fine. I imagine you probably don't. But if you look back in your notes from chapter 6 on beam bending, when we derived the flexure equation that the stress is MC on I, to do that, we looked at, okay, fine. So here is the undeflected curve. And then if a little chunk of material deflects up as follows, kind of exaggerating this, right? This is dx. We were able to relate the strain and then the stress through to the curvature of the beam, right? So rho is the radius of curvature. So that's the radius of curvature at a point. Yeah, it says right here. And the inverse of that, 1 over rho, is the curvature. Sometimes they use the Greek letter kappa to denote curvature, and that's 1 over rho. All right. And we developed this relationship. Okay. All right. We also had from that the strain itself was minus y over rho. Okay, we had that as a starting point, right? Okay. Actually, I think I should probably start with this. In order to derive this class, I would start with this. You know this. You know that the strain is equal to the stress over Young's modulus. And we know the stress is negative MC on I, or negative MY on I. This is minus MY on I. So if you put that in here, you get, oops, I'm sorry, negative MY on EI, right? The Y's cancel out. And here you can see we get, and the minus ones cancel out. We get minus rho equals M on EI, right? Which is, we got there, right? So we have that relationship. We can relate the curvature, 1 over rho, through to the bending moment at the point, as well as Young's modulus and the second area moment, I. Right? Now, also, if you go back to your calculus class, look at this. When they do talk about slope and deflection, they give you the exact, nonlinear relationship between the curvature and the derivative of the slope, and that's there, right? So it's got this first derivative of the slope over that, 3/4 root of the slope squared plus 1. So this means that 1 over rho is approximately equal to the derivative of theta with respect to x. And we remember that theta is also equal to the derivative of v, right? So this means, this gives us that 1 over rho is approximately equal to the second derivative of our deflection curve with respect to x. Okay. All right, so you can take that information, right? We can put it into here, and now we get that the moment over EI. I'm going to drop the approximation because we always, these beam deflections are all really small. And this equals the second derivative of V with respect to X. Or, this is the first derivative of theta with respect to X. Okay. So we get that relationship, all right? And I'll show on the next slide. We can actually get that into this fourth order differential equation. Let me not do that just for now. But so we got this, right? We got this relationship. I need another page because this is this, right? Let me erase a little bit on this page, okay? And we'll just get to that differential equation. So let's erase this stuff. Yeah, I apologize for doing this on PowerPoint. It's like weird doing this on PowerPoint. Easier doing this on a blackboard. Okay, so here we go. We got this. We're going to start off with the fact that m over EI, or actually, let's multiply by EI. It's not a big deal. So I'm going to go here and go up here. So m, I'll multiply both sides by EI. This gives me EI, second derivative of the deflection curve with respect to x. All right, now, if you also remember when we did the shear and bending moment diagrams graphically, we knew that the derivative of m with respect to x was v, correct? The shear diagram, the value of the shear diagram is equal to the slope of the moment diagram, or what we did actually there is we integrated. And so I could just take the derivative of both sides up here, and this is d dx of this whole mess, the EI d squared v dx squared, right? And we also knew that the derivative of v with respect to x, that was equal to the value of the distributed load, maybe it's 0, at that point, okay? And so again, we can take the derivative of this again, and that finally gives us the second derivative with respect to x of EI d squared v dx squared. All right, so that brings us down to this differential equation, all right? So it's a fourth order differential equation. It involves the fourth derivative of v of x. If E and I are constant, you can just see the EI would come out. But technically, if E and I change along the length of the beam, you have to take the second derivative of those. But most often this is constant. It can come out. But it's the fourth order differential equation. It's a linear differential equation, but it is fourth order. So you could actually integrate 4 times and get v. So for example, let's assume EI is constant. I get the fourth derivative with respect to x of v of x equals the distributed load over EI. So I could just integrate this 4 times basically and solve for the deflection curve. And that's it, all right? It's almost the same way we did to start from the distributed load W of x, get the shear diagram V of x from that, and then graphically integrated that to get the moment diagram, okay? We would actually integrate it once more to get the slope, and a second time to get the deflection. Okay? All right. So don't panic too much. You're not going to be doing too much differential equations in this class, but that's what it is. And this is why they kind of kick it to its own chapter as opposed to just covering a section in chapter 6. All right, if you remember when you solve differential equations, you need to have boundary conditions. And so you actually, whatever order your differential equation is, you have to have that many boundary conditions. Basically, those are the constants of integration. Each time you integrate this fourth order differential equation, you produce a constant of integration. So you're going to integrate it 4 times. You're going to produce 4 constants of integration. That makes it only unique if you can give 4 boundary conditions that allow you to solve for those constants of integration. And fortunately, they're pretty easy to deal with. There's a lot of different boundary conditions, but I just used the picture in the book to kind of show you. So for example, we've got like these are basically the same. It's a pin or a roller. They're ostensibly the same for beam deflection, right? And if you look at this, at the point where we apply the roller or the pin, we know that the deflection curve has to equal 0. V equals 0, all right? Also, because of the shear in the moment diagram, we know the shear at this point has to equal the reaction force, and there is no external moment, nor can the pin or the roller support a moment. So the moment is going to go to 0 at that point, and the shear is going to equal the reaction force through the pin or the roller in the y direction. Since the moment is 0, if the moment is 0, right, and we know that, recall right from here, if the moment is 0, that means the first derivative of the slope has to equal 0. That's what we have there. Okay. Now, if the pin or the roller is in the middle of the beam, you can't make those relationships because you actually have the internal forces of the beam acting on that as well. Okay? Another case we might have is the beam could be fully fixed. And if it's fully fixed, in this particular case, right, not only is the deflection equal to 0, but the slope of the deflection curve at that wall is also equal to 0, right? You cannot have any rotation at the point where it meets the wall. And the moment is going to equal whatever the moment boundary condition is by the wall, and likewise the shear is equal to whatever shear force the wall resists on it, okay? And so those give us, you know, in this particular case here, right, 4 boundary conditions. Those are 4 boundary conditions that we can invoke on this problem, okay? All right. So, like, how do we solve these problems? How does this go? Well, like I said before, the easiest way to think of it is it's a 4th order differential equation. So we're going to integrate it once, twice, 3 times. Well, actually, I should say 4 times, right? We're going to integrate it once to get this, twice to get this, then this, and then this, okay? So 4 different integrations to finally give me V, all right? So let's say we have a beam with a uniformly distributed load. Let's say, for example, you have something that looks like this. Okay, so we're built in at one wall, and we have a constant here, right? So that's a constant. So here is our distributed load curve. We already know that if we integrate the distributed load, we get the shear curve, or in other words, the slope of the shear curve has to equal the value of the distributed load. And so we were able to construct the shear diagram. This looks weird. This is supposed to be a quadratic. I do not know how to draw a quadratic in PowerPoint, so whatever. But likewise, we also were able to integrate the shear diagram and get the moment curve. So in this particular case, the moment is a quadratic. The shear, oh, actually, I should do this differently. Yeah, actually, I didn't draw. This is actually drawn enough for this beam. This should be for, let's do it this way. It's actually for this beam. Whoops. Let's not do this beam. We're going to do this beam. I'll explain why in a second, right? So here's it's a constant, okay? All right. The reason is because at this point here, the shear force vanishes. There's no shear force. And likewise, there's no supporting moment. So the moment vanishes here, right? So you just get this. And then this value right here is going to be the shear force applied by the support. And this value of the moment curve here is going to give you the moment that's supported there. All right. So we were able to do this in chapter 6, right? You guys are experts on that. All right. You know how to do that. Nothing's changed. But now we're going to do the process 2 more times, right? So fine. So we have m of x. Now we added this equation. This is actually the elastic equation, but it's written in terms of theta and m. So similarly, I guess it might be easier if you were to take m and divide by ei. You could get the slope, right? So let's look at this. All right. So we know here at this boundary condition that v of x has to equal 0. And we also know that the slope has to equal 0 because of the boundary condition that's built into the wall, right? So we know the theta is going to go to 0 right here at the right-hand point. And, you know, this is a quadratic. So if we integrate it again, you're going to get a cubic, right? And what happens? It slopes down. And so you would expect to see a negative slope that increases, or sorry, decreases cubically. So maybe I should draw this one. Oops. So we start here at 0, and it's going to go down as a cubic. This is going to be a cubic, right? So again, you're just integrating it, and don't forget to divide by, you know, the EI, right? We have to divide by EI, right? And then once you have the slope curve, you can again integrate it because we know that the integral of the slope is the deflection, or in other words, the derivative of the deflection is the slope. So in this particular case, we know that v of x is going to be 0 at the right-hand side, and it is going to deflect down as follows. And this is going to be a quartic equation, right? Fourth order polynomial, okay? All right. Do I actually do the numbers here? I do the numbers. I do the numbers for that condition. Okay, well, that's fine. I guess I should have stuck with this. Okay, whatever. Oh, this is different. This is using a tip force. All right, well, let's do this. This is actually doing it with letters. I mean, you could use numbers as well, but this is a little different case. Okay, so here's another example, right? So let's say we have a beam here. It has, you know E, I, it's got a length L, and then there's a tip force of P applied there, right? And we have the boundary conditions. It's built in on the left-hand side. So the slope and the deflection are both 0, right? So right here, v of x is 0, as well as the derivative of v of x, or the slope is 0, right? Okay. Well, let's do the first 2 integrations. Remember, the first integration is going to give me the shear curve, okay? So basically, the shear curve, well, right, to get this, right, we know that the derivative of the shear curve equals the uniform loading, or the distributed load. In this case, the distributed load is 0, right? There is no distributed load on here. So the slope of the shear curve is 0. It's straight. Okay, we know it's flat. And the first integration constant is such that on the right-hand side, we know the shear force has to equal P, right? So that means that you're going to have uniform shear across the entire beam, and it's going to equal P, the tip load, right? So here's our V of X curve, flat. All right, and again, we know that the derivative of the moment curve equals the shear curve, or we integrate it, right? So when we integrate a constant, we get a linear, and the slope is going to be P. All right. Now we also know that at the tip here, right, at the very end, there's no external applied moment. This is the boundary condition. So the moment curve has to go to 0 here, right? So we're going to start at 0, and it's a straight line with a slope of positive p. So this is a slope of positive p. And that means that the moment down here is going to be minus PL, right? So we can either formally integrate it, or you can see it from this plot, that the moment curve is just P times X minus L, right? So if we use X equal to L, we get 0 here, or if we put an X equal to 0, we get minus PL, okay? Again, this is exactly what we did in chapter 6. All right, so now we're going to do that again, but we have to divide by EI, right? So basically, that's what's going on here, right? So the slope, right, is we divide by EI, and then, or we integrate and then divide by EI, right? So there you go. And we know that at X equal to 0, the slope is 0. So if we do this integral, knowing that the moment is P X minus L, take the antiderivative, you're going to get that relationship, right? P on EI is X squared on 2 minus L times X, right? There should be there should be a constant of integration there, right? But, there's a constant of integration, but we have to use the fact that the slope goes to 0 at X equal to 0. So if you put in X equal to 0 here, you're going to get the fact that the slope goes to 0, right? And you can just massage it again like that, right? All right. And then we can do it one more time. We integrate again. And this will give us the deflection curve. Okay. It's going to be cubic. Right? No, whatever. So we have our slope curve. And then we're going to integrate it again. Here's the antiderivative. Again, there should be another constant of integration here. But we need to apply the boundary condition that for this particular problem, the deflection at X equal to 0 is 0. And so if we put X equal to 0 into this equation and want it to go to 0, that's going to give us that C1 has to equal 0. Okay? And so that integration constant goes away. And then that finally gives us the final deflection curve here as follows. Okay? And again, if you had numbers, you would have numbers for P, E, and I, and L, right? The same difference. Okay. Why do I think I should have an X on L? Oh, that's right. That's right. And obviously, probably most interest is what's the maximum deflection at L, and just put an X equal to L and you get the following, right? So this value down here is going to be minus PL cubed over 3EI. So they're going to tend to be quadratic relations. They're going to tend to be polynomial relationships, right? So when we had the distributed load as constant, then the slope is a linear, the moment is a quadratic, the slope is a cubic, and then the deflection is a quartic. When we started off with just the tip load, the shear is constant, the moment is linear, the slope is quadratic, and then the deflection is cubic, okay? So it's just keep integrating the elastic beam deflection curve and you'll get your answer, okay? But you have to be a little careful with the boundary conditions, all right? Okay. So let's do this example. Let's do this. I don't know if I want to do this on here or not, right? Do we have enough room here? I should probably just do this on the example problem. Let me do this on the whiteboard thing because I always have a tough time. The PowerPoint thing don't work so well. All right, so let's solve this. I'm going to shift. Can this work? Let's see. No, that's not the one. Dang it. That's the other one. Where is it? All right, let me stop this. Copy. Maybe it'll work if I do this. There it goes. All right. All right. So after all that delay, I just was able to open the problem in this thing where I can write easier. All right. So here they want us to find the deflection at the end at C. All right. So it's a circular shaft. It's 100 millimeters in diameter. So we can get that I is pi over 64 diameter to the fourth, right? And so if we do that, that gives me, let's just do, yeah, let's do everything in meters. Units always get a little weird when we do the deflection stuff. Fine. All right, so I get I is equal to 4.91 to the minus 6. That's meters to the fourth power. Maybe we'll write it. Doesn't want to draw it. Why? There you go. All right. All right. And so we want to find the deflection. E, they give us as 200 gigapascals, right? All right. So first, we have to get the shear curve, the moment curve, then integrate that again, get the slope, and then integrate that again and get the deflection. And we're going to apply the appropriate boundary conditions. It's a little trickier here because in this particular case, we know that the deflection at x equal to 0, that's at point A. This is point A. That is equal to 0, as well as the deflection at x equal to 2 meters. That's point B. That also is equal to 0. Okay, so those are our two boundary curves boundary conditions that are going to allow us to integrate from the moment to the slope and then from the slope to the deflection. Okay. All right. So first we got to get the moment curve. All right. So first we got to get the moment curve. All right. So let's see if I can do this somewhat neatly. Maybe I can't. All right. So we have this point, and this point. So first I'm going to do the shear diagram, right? The shear diagram, the force is going to go up. Yeah, so we're going to have a lot of negative. I think it's mostly going to be negative. Whatever. All right, so let's figure out the reaction forces, right? So we're going to have here AY and BY, correct? So in this particular case, let's do sum of moments around, whatever, we'll do them around point A, I guess, right? Equal to 0. So that's going to give us by is a negative moment, so minus by times 2 meters. I'm sorry, that's actually a positive moment, right? Positive moment. And then the 6 kilonewton is going to be a negative moment, right? And so that's or equals 6 kilonewtons, and its moment arm is the 3 meters, right? So that gives us that by is equal to 3/2 of the 6 kilonewtons, which is 9 kilonewtons, right? And then we can do sum of forces in the y direction equal to 0. So that's going to give us AY plus BY, which is 9 kilonewtons, equals, or minus 6 kilonewtons equals 0, right? And so that's 3 kilonewtons. So AY equals minus 3 kilonewtons, correct? All right. So, so actually AY is actually going to go down this way. So we got 3 kilonewtons acting that way. And then we have the 6 kilonewtons the 9 kilonewtons acting up. 9 kilonewtons acting up here. Okay. All right. So if this is 3 kilonewtons acting down, that means just to the right, you're going to have 3 kilonewtons acting up. So that's actually a negative shear, right? So let's give it this. So if we were to draw here, V of X, the shear, here is X. So we're going to start off at 3, minus 3, I should say. Well, actually, maybe this is, maybe I should do it this way. Maybe it's more in the middle. 3, that's about 6. So we're going to start off here at minus 3. And so we're going to plot everything here is going to be kilonewtons. And then at point B, it's going to go up 6 kilonewtons. So that's going to, it's going to go up 9 kilonewtons. So that's going to take me to 6 kilonewtons up here. And then pop back down by a negative 6 kilonewtons, which brings me to 0 at point C. So it's going to look like this. Okay, so that's our shear diagram. All right, that's the shear diagram. All right, so now let's get the moment diagram. All right, so the bending moment, we know, right, has to vanish at A. There's no external bending moment there. And it's also going to vanish at C. There's no bending moment external at C. At B, there will be a bending moment because it's, that pin is in the intermediary point, but there's a bending moment that just happens because we have reaction forces on the right and the left, okay? But we know that's going to go to 0. And if you think about it, it's going to bend in the following manner. So that is a negative bending moment. So these are all going to be negative. It's going to be all negative. So here's X. We're going to plot the bending moment. And it's going to have units of kilonewton meters. All right. Okay, so we start off at 0 here, right? And and then we're gonna it's going to be quadratic, right? The slope is starts off as negative and then becomes positive, okay? Right, because remember, right? The, the derivative of the moment is equal to the shear curve, right? So we're going to start off at 0, and the deflection is going to be negative. Start off at like -3, and then up at point B, it's going to be positive. It's going to be 6, so it's going to be greater. And so this is going to have a shape that kind of looks like this. Oh, I'm sorry. It's not going to be 0. Like we know that the slope here is 0, right? So here's our, so it's going to go like this. Or it's going to do something like that, okay? So let's figure out the points, right? So right here, this point here is going to be 1/3 of 2 meters. So this is 2/3 meters, right? That's right there. And what do we got? So it's going to go to 0 there. We can get the bending moment, right? That area is going to be -3 times 3/2. So that's 2 kilonewtons, and then 1/2 of that. So it's going to be this is -1 kilonewton meter. That's going to be the value there. And then we're going to go up this area here. So this is -1 kilonewton meter. And the area under this curve is going to be, what is that? That is, oh, why am I calling this 2/3? Yeah, no, that's right, 2/3. So that area is going to be 1 1/3. 4/3. This distance here is 4/3, right? 4/3 times 6. Third divided by 6. Okay, so that's 6. So it's 4, right? So it's 4. Wait, no, again. 4/3 times 6 divided by 2, 4. Yeah, it's 4. So this area here is 4 kilonewton meters, correct? That's the area there. And so if we start off at -1, we're going to go up that 4. So this will put me up here at 3 kilonewton meters, right? And now we have a negative slope, right? And it's going to go down. It's going to start off with a negative slope of 6, and it's going to go down to 0. So it's going to do something. It's going to do that. No, I'm sorry. What am I doing? Wait a second. What am I doing here? This area here is 1 times 6. This is 3 kilonewton meters, right? So it actually has to go like this. It's supposed to go like this. Where's this supposed to do? What am I screwing up? Oh, yeah. Oh my gosh. Don't you guys stop me. All right. You guys. So what did I do wrong? Does anyone know? Why did you guys should have stopped me way earlier? Nobody? Is there anybody there? All right, whatever. All right, I'll speak to myself. All right. I'll just do this myself. Just no one's listening. All right. So I screwed up the shear curve. I don't know why I did it that way. That was just dumb. All right, so let's go back. I screwed up the shear diagram curve is piecewise constants, right? So 3. So yeah, like this. All right, so let's do it again. Here is x. This is the shear curve, right? The shear curve starts off at -3. It's constant all the way to here. It bumps up 9, takes me to +6, and then goes like that. Okay? And then takes it down to 0. All right? So this is all negative, and this is all positive. All right? Now we're going to do that, and the moment curve is going to be linear, right? The moment curve is going to be linear, right? So now we're going to go do the moment curve, which again is 0, down and up, right? So it's going to look like this. So again, here is x. Now we're going to plot the moment curve, which is going to have units of kilonewton meters. All right. So it starts off at 0 because there's no external moment there. And it's going to have a slope of -3. So this area here, what is that? That's 2 meters. So the area under this first triangle is, this first area is 6 kilonewton meters. And this is also 6 kilonewton meters. All right. So it's going to kick down to -6 kilonewton meters and then go back up to 0. So it's going to look like that. All right. So that is my moment diagram. All right. The max bending moment happens at point B, and it's going to be -6 kilonewton meters. All right. All right. Okay, fine. So now we're going to use the relationship that right? The derivative of the slope curve is equal to the bending moment over EI. All right. So that means we're going to have a piecewise quadratic, if you will. Okay. So what's going to look like, right? Let's kind of sketch it out again. Let's bring these points down. So think it's going to be kind of mostly negative. It's mostly negative. So here's x, and now we're going to plot theta, okay? So this is going to be in radians, right? It's dimensions. So we're going to do radians. All right. Okay. All right, so it's going to be, so let's talk about what the shape of this is going to be, right? So since the moment is a linear, if we integrate it, it's going to give me a quadratic, right? So they're going to go quadratically, right? And, you know, if you think about it, it kind of makes sense, right? You know, we have a pin here and then a pin here and then a force here. So we expect the elastic curve to go like this, right? We expect it to go like this, all right? And so if that's the elastic curve, if this is v of x, right? The slope is going to start off as a positive value, right? It's going to start off as a positive value. It's going to go to 0. Slope here goes to 0 and then becomes negative at this point. Down to this point, right? Oh, I'm sorry, what am I doing? So that's 0, and then it's going to continue like that down through like this. Okay. Okay. So we don't know what the slope is here, right? We don't know what the slope is at this endpoint, right? Because that's part of the integration constant. And it's going to go 0 somewhere. Which again, we don't know, right? We don't know that, right? Right. Okay. But if we were to look at this region, right? In this region, we know that the moment is equal to minus x minus 6x, what is it, minus 3x minus 3x, and in this, right, because it starts off at 0 and then it gives me minus 6 at 2 meters, and then here the moment is going to be the slope here is 6, so it's going to be 6x, and at 2 that's 6. Is that correct? No. Right. So here it's 6x minus 18. If you put in x equal to 3 at the right point, it goes to 0. If you put in x equal to 2 right here at point B, you get 12 minus 18 is minus 6, right? So if we were to piecewise integrate those, right? So we know that, where's my, right? All right. Okay, sorry, someone's calling. Let's do it this way. Derivative of x is going to equal 1 over EI minus 3x over EI. This is for x between 0 and 2 meters, right? So this is going to give us in that first region that the antiderivative of this theta of x is going to equal minus 3x squared over 2EI plus some constant of integration. I'll call it C1, right? This is between 0 and 2 meters. And likewise, we know that this is going to have to equal 6x minus 18 over EI from 2 meters out to the 3 meters, right? So if you integrate this again, right, this is going to give me theta equals, or theta of x, I should say, right? Um, 1 over EI, 6x squared on 2, which is 3x squared, minus 18x, plus, again, a constant of integration. I'll put the constant of integration right here. Actually, it's usually easier if we put the constant integration inside. So I'm going to put EI over this constant integration too, just to make life easier. All right. Okay. So fine. Now from this one, right? Well, actually, this is all we got. But we do know that we have a continuity requirement. If we look at point B right here in the middle, right? We know, or right here at this point, the slope coming from the left-hand side, the minus side, has to equal the slope coming from the right-hand side. So we got a continuity issue. So these two relationships have to equal at x equal to 2, all right? So if we take this and solve it at x equal to 2, we get the following, right? We get minus 6, 2, 4, minus 12 over 2EI plus C1 over EI. And that has to equal this equation at x equal to 2. So that is 1 over EI. So I take the EIs out of everything because they all just drop out. 3x squared, 2, that's 4, so that's 12, minus 18 times 2, 36, plus C2, right? So the EIs all cancel out. And here, you can't solve for C1 and C2, but you can solve for like C2 in terms of C1, right? Here we can get that C1 equals 12 minus 36 plus 12 plus C2. So this is 24 minus 36 is 12, right? So C1 equals C2 plus 12. And I know I'm at the end of the class here. So there we go. That's what we have now. So from here, I still have a constant integration. I got that theta of x is going to equal the following. But everything's in terms of C1. So my first, from 0 to 2 meters, we have this equation. Come on, stop doing this. All right. So it's going to be 1 over EI minus 3x squared on 2 plus C1, which I still don't know. And that's from 0 to 2 meters, okay? Then from 2 to 3 meters, we're going to use the second relationship. Where is that? This one, right? This one. But we know C2 in terms of C1. So this is going to be 1 over EI, right? 3x squared minus 18x plus C2, but we know C2 is, well, C1 minus 12, right? So this would be plus C1 minus 12. And that's from x between 2 meters and 3 meters, right? So I still have the single constant of integration here, but now I don't have time to do it here, but what we're going to do next is then take this and get that the deflection curve v of x is equal to the integral of the slope with respect to x. Okay. Again, we're going to have to do it piecewise because we have the discontinuity at the intermediary pin joint, but we'll have another continuity equation, right? V of xb just a little bit to the left has to equal the v at xb just a little bit to the right. And now we can use also that we know that v of xa has to equal v of xb, and that has to equal 0, okay? So we'll get two more constants of integration, but we'll be able to solve for those out in there, okay? All right, I'm going to stop now. So I apologize for not getting through that problem. All right, we'll finish this up on Thursday.